Hello, welcome back. In this segment, I will prove a very important lemma we need for the next few segments. This is regarding the number of elements in a group which would have a given order D. Notationally speaking, NP of D denotes the number of elements of order D in the group Z star P. Z star P means all the elements from 1 through P minus 1. Okay. And pi denotes the Euler's torsion function. So the lemma is that if we know for sure there exists an element of order D, then the number of elements in the group Z star P with order D is nothing but pi of D. Before I prove this, I wanted to give you an example so you get an idea of what I'm trying to prove. So here is your residue. How many elements have order 5? We can look at the fifth column and see how many ones occur. Okay, we can see element number 3, 4, 5, element number 9. There are 4 elements with order 5. And what is pi of 5? Euler's torsion function is also 4. So the lemma that we mentioned on the whiteboard is true for one particular element we checked. Let's select how many elements have order 10. We just look at the last column. Here is 1, right? 1, 2, 3, and 4. Okay, what is pi of 10? Pi of 10 is also 4. So you get an idea now that measuring the pi of the order gives you the number of elements in the group that would have that particular order. The case is extremely simple if we consider D to be 1, right? If D is 1 means element has an order 1. So only 1 has order 1, right? And what is pi of 1? Pi of 1 is also 1 by definition of Euler's torsion function. So we can leave out the scenario that D is 1. That's easy to prove. Now consider this scenario that we are given enough NP of D is greater than 0, right? That means there must be an element A with order D, okay? With order D. If I call the function order just to denote the order of the element, it must be order D greater than 0. There must be an element, right? Otherwise, they wouldn't have given this precondition here. Okay. What can we say if an element has an order D? This implies A power D is 1. All right. This is basic definition of order. Now consider this polynomial, x power D equal to 1. How many roots can this polynomial contain in Z star P? We proved earlier that a polynomial of degree D will have at most D roots in ZP. Okay. So in the group ZP, we already proved that. So this means we should be able to conclude that there can be at most D solutions for this polynomial x power D equal to 1. Okay. If you put x is equal to 1, 1 power D is 1, obvious. So let me write the set of all solutions are 1. A is a solution because A power D is 1, right? That's the definition of order of A is D means. Okay, if A is a solution, A square will also be a solution because A square, if you put x is equal to A square power D means A power D square. A power D is 1, therefore A square is also a solution. All the way until A power D minus 1. Okay. Right? These are all the possible solutions for this polynomial x power D equal to 1 in Z star P. Okay. And now we ask this question. Again, we go back to this polynomial x power D equal to 1 and ask a question. How many elements do we have in our Z star P that will satisfy this equation? We have clearly seen from the definition that all elements that have order D will satisfy this polynomial, the one that I have put in the box. But these are the only possible roots for this particular polynomial. Okay, that means we have to count how many elements in this set have order D. Okay, if any element in the set has order D, this equation will be satisfied. So how do we find how many elements in this set have order D? Okay, in the one of the previous segments, we proved this fact that if order of A is D, okay, let me recall this very quickly. If order of A is D, okay, what can you say about order of A power K? So now we pick an element here. Let's call that element to be a power k, where k lies between, say, 1 less than k less than d. Now, I'm avoiding k to be 0 because we have already proved the fact that when d is 1, we know the theorem is true. So there is no reason to consider k to be 0. Okay. Now consider only the k value from 1 through d, excluding d. Order of a power k is nothing but d by gcd of k comma d. So if you want order of a power k to be also d, what do we want? We want the denominator to be 1. So if the denominator is 1, then the numerator is the answer, right? When you divide the fraction. So you get d. So how many such k's will have a gcd of k comma d to be 1? That's just the definition of pi of d, right? Pi of d is the definition that tells us how many k's exist between 1 through d, excluding d, such that gcd of k comma d is 1. This thing has to be 1 for us. Okay. So we are going through this set and we are counting how many powers of a will have this property that gcd of k comma d is 1, where k is the power, k, this is power 1, power 2, and so on. So we are just counting that. That's nothing but pi of d. That's the definition of Euler's torsion function. So what did we prove? We proved that there are pi of d elements with order d in the group Z star P. That's basically it. Thank you very much.